Welcome to episode or part 2 of the ATtiny adventures, and in this part we will be discussing expanding I/O. If you have a small micro controller like this ATtiny, it's got 8 pins and up to 6 I/O pins, which can be used for various purposes. We see SCL and SDA. We know that belongs to I2C, which is a 2-wire serial interface with a particular protocol. And also any of the other pins, of course, can be used for some other kind of serial output, which we're actually, in this little sample here, we're actually using that with a shift register to actually output up to 7 segments plus a decimal point. There's 8 different LEDs in there. From in this case, the shift register needs 3 pins of the ATtiny. But over here on this little board, we have a PCF rather 8474, and that is a dedicated chip for providing expanded I/O for microcontrollers, and it can be used on all microcontrollers, of course, if you need extra pins. This is the 8-bit version. There is also a PCF8575, I believe, that has 16 I/O pins, and we'll be discussing that in the various parts of the video coming up. And so following this intro here, there will be several videos which are collected over a period of time doing various different projects with the ATtiny, just trying out what is available. We run into a few frustrating things about it, but I've been able to solve most of those in various different videos. So this video is going to be fairly lengthy because of that. I have different videos for each one of these. Typically I'll make up a circuit on a breadboard like this and describe the circuit and the actual software that runs it and so on. So I will put chapter markers in, and also I will put the locations in the actual description if you look for it there. If you have any comments, or if you, I am just actually doing this as an investigation myself, so you're actually along with the experiment here with me, because a lot of this stuff is new to me too. And if you see that I'm doing anything wrong or something can be done better, please put it in the comments so that we can all know what we can do in a better way if you know anything. So let's, with further ado, let's go and check out the other videos that are following it. You will find that with this ATtiny, it's like the Wild West out there. Much information is actually completely out of date. It might be 6 or 8 years old, and the situation has changed a lot. There's a new version of the Arduino IE, and that has a bearing on things, and so on and so on. So let's have a look what I found out. Okay, so this is one option. When you have a small microcontroller and you want to control more than the outputs than what the microcontroller has, you can use a chip like this 4099 CMOS chip. They call it an 8-bit addressable latch, but it is actually quite a flexible device. Being CMOS, it can actually handle high voltages than 5 volts, up to 20 volts by the looks of it. And this particular device only has one data pin, so therefore it's like serial data input. So that only is one pin on your microcontroller. Then there is 3 address lines that actually individually address Q0 to Q7. So you can tell it which output pins that you want to change by setting the data pin. So they say it has active parallel output, storage register capability, can function as a demultiplexer. That's what we're going to be used as a little demo just for fun. And there's a little diagram over here again. You have like 1 byte, 8 bits coming out. You can address each individual bit with these 3 address lines, and you can set the data to high or low on those address lines according to what you put on that pin, and it has a reset and a write disable. Okay, so this is the a little truth table over here, mode selection for the 4099, and this is the WD, and in the circuit it's going to be called WR, but it's the same thing. And this is the reset pin. Remember, you will see that we are pulling WD permanently low connected to ground. So we're using these particular modes over here. We're going to be using as a demultiplexer. So when the two are low, depending on what you've got selected on A0 to A2, will actually, the selected output will follow the data pin. So if it's high, it will be high. If it's low, it's low. But all the other Q output pins will be held to the previous state. They won't change. If reset is 1, it will actually, it still follows the data, but as soon as the data is selected, all the other pins will be reset to 0. Now, if I was using this in a proper circuit, I would want to actually also connect the WD pin to something and make sure that it gets set to 1 with the reset pin set to 0, so it can hold its previous state. That would be useful if you're using it as like a register and you want to put an output on it, an 8-bit output, and you want it to stay stable. But we are just using it in this mode over here. So let's have a look at the circuit. So this is the circuit that we have wired up on our breadboard. I've only put the ATtiny on the circuit here because that's what normally you would have. You would program your ATtiny and then it would be plugged into your circuit. But for this particular test, I am using the Digispark board, which of course has some extra components in there as well, like a diode and some LEDs, some capacitors, and some voltage regulator, etc. So they can be ignored because they are only used just during the programming and stuff. If this was a real circuit, indeed, you would want to put some decoupling capacitor across the ATtiny and so on. But for this particular exercise, just to see how the circuit works and is connected, this is good enough and keeps it simple. So also keep in mind again that the actual physical pin numbers, which are the red ones over here, are entirely different from the PB0 and then on the Digispark board that is actually going to be called P0, connected directly to the ATtiny. And in the sketch, indeed, we will refer to this as pin 0, 1, 2, 3, 4, 5, but the physical pin numbers are actually 5, 6, 7, 2, 3, and 1. So keep that in mind. I wish that in the sketch they would have had, or in Arduino they would have defined the pins names as PB0 or even P0 or something like that, but they just use the number 0, 1, 2, 3, 4, 5. So therefore you've got to keep that in mind. Okay, so we are using these 5 pins over here as output. As you can see, they're pointing away. This P0 is going to be defined as an input pointing inwards, and the reason for that is that P0 is connected to this push button here, which has got ground on one side and a pull-up resistor on the other. So when we push the button down, P0 will go low, and it'll be an input to PB0. A0, 1, 2, and 1 and 2 are connected to P3, P2, and P1 on the ATtiny. We are pulling the WR pin permanently low, so it's always going to be low just for this exercise. The data pin over here, I might as well have connected that data pin to plus 5 volts actually, but I connected it to P4, so we have to therefore set it in the sketch to high as well. This is the reset pin, it's going to be P5. The outputs, we're only using 3 of the output pins just for this little exercise, because I've got it connected to an RGB LED, which actually internally has 3 little LEDs in it, a blue, a green, and a red, which the cathodes are connected to ground through a resistor, and Q3 to Q7 we're just not using. And so that's circuit's very simple. It's wide straight across. So let's have a look at the code next. Alright, so code is pretty simple. For some reason they call them a sketch in Arduino world, I don't know why. But first of all, we define some defines here. To define those pins, we will actually give them names rather than numbers. Remember, this is PB3, PB2, PB1, PB4, PB5, PB0. As I said earlier, they're not physical pin numbers. But rather than using hard-coded numbers, it's much nicer to give them names so that we can see which is what. Okay, so we got a little variable here, count, that we're going to be using to toggle between the little LEDs. And here we have the button that's going to be an input, the A0, A1, and A2 that we're going to be using on the ATtiny that's going to be connected to the CD4099 is going to be all outputs on the ATtiny, inputs to the CD4099 of course, and so it is with the data pin and the reset pin. So this I'm toggling the reset low and then high so that it can actually reset. Not sure if that's really necessary, but works, so I didn't change it. Count's going to be initialized to 0, and we're going to initially write 0 to the 4099, and we have a digital write to reset, set it low. Then we're going to set the address pins. Now A2 is always going to be low because we're only using the 3 output pins, remember. So if the address is too high, then set it to 2. It's good practice to do that in your code, but it should of course never happen. And if address is 0, then both A0 and A1 is going to be low. Otherwise, if it's 1, A0 is going to be high and A1 low, and if it's 2, A0 is going to be low and A1 is going to be high, and then we can make sure the data is high. As I said, I might as well connected that pin to plus 5 volts anyway, but still. And then we toggle the reset high again. Then in the loop here we say digital read button. If it's low, in other words it's down, then increment the count. If it's larger than 2, then make sure it toggles back or rolls back to 0, and write to the 4 zeros are 9 the count, and delay to 50, rudimentary debouncing, and that's all there is to it. So let's switch to the other camera and see if it works. Okay, so here's our little circuit on our breadboard. As I said, I'm using this Digispark board over here, but the output pins here, P0, P1, 2, 3, 4, 5, are right there, and they're coming directly from the ATtiny, which is this thing here. And I'm not using the voltage regulator on the chip here. I'm just feeding this thing with 5 volts from my bench power supply. And if I push the button here, went from blue to green, green to red, back to blue. Works just fine, as you can see. So we are in business. So this is one way that you can interface a small microcontroller with some chips in order to expand its output a little. But this is only an output, and there are other chips, of course, which are both input and output, and we'll look at those next. So another device that is commonly used to connect to microcontrollers, such as our ATtiny 85 here, but it can also be used on much larger microcontrollers that have lots of outputs, is a shift register. This particular one is a 74HC595, and it is actually it's a high-speed CMOS device, and its features is such that you only need one pin for the serial data to come in, which is connected to PB1 on our ATtiny according to this diagram that I made up. That's how I hooked it up. And then you have a clock which is connected to PB0 coming in at this SR clock signal over here. And the idea is that you actually have a serial input, and the clock actually tells on, I think it's on the leading edge or something like that, it tells the chip over here when to actually look for whether the data coming in is high or low. So then we have it's called R clock here, but it's actually a latch signal which is connected to PB2, and it actually enables or disables the output. So you'll see in the software we'll be using that to actually disable the outputs while we are sending in serial information, so you won't see anything changing while that is happening until it is finished. So then we have these 8 outputs over here, and we have that going to some 150 ohm resistors, and I've decided to use a 7-segment display. Well, it has 7 segments plus the decimal points, actually 8. So instead of putting 8 separate LEDs on there, we'll be seeing this display going to all these different motions, and we're going to be using this display for yet another chip later on, so it's already convenient to have it already there. Few 8s on this one here is actually pin 9. We're not using it, but this could be connected to yet another HC595. So if you were sending in 16 bits of serial information instead of only 8 bits, then the overflow would come out over here, which can be put into the serial input of the next chip, which can share the clock input, of course. And then you have a 16-bit latch data on the output, and you can have 24 bits and 34 bits. You can expand it as many as you might need. I'm not sure if there's much else to say about it. It is fairly simple, in actual fact. There's an output enable which is active low. We permanently connect to ground in our little test here, and we have a clear signal here. It's like a reset, I think, which is also active low, so we connect it permanently to the plus 5 volts, so we're not actually using that. And that's basically it. And then we load a little sketch into the ATtiny 85 to actually output serial data into this chip, which we'll look at next. So we are using the PB2 pin, which is the number 2, and we're calling that latch. Clock is going to be PB0 and serial is going to be PB1, and a temporary little integer there to count. We set the pin modes all to output on these on the ATtiny, and that's supposed to say 255. So we can actually put, if the count is larger than 255, then set it back to 0. And I'll put an extra little delay in there so I can see it happening, so I know that it is starting back again to 0. And we do a digital write on the latch, set it low, so that we're disabling the output while we're changing the input, so we don't have any noise coming out of there that might confuse us. Then we actually use the shift out command to do a serial output with the most significant bit first on the actual clock signal there. Then we do a digital write of the latch and set it back to high, so now it can display the value that we have actually sent it, and we're going to the next count, delaying a quarter of a second, and then the whole thing goes back over again and it will run forever. So let's upload this to our ATtiny, and it's done compiling, so it likes that. Let's save the file while we're at it, and now I'm going to hit the upload, and now I need to plug the ATtiny in. Okay, it's done. So turn it on, and let's have a look if it works. Now PB0 is actually the data output, and it also happens PB1, I'm sorry, and it happens to be connected to a little LED on the little Digispark board that we are using, so that's why you see that flashing there as well. And you'll see that this will go through all the different combinations of bits, LED bits, so it goes through all the different combinations that as you can see. So everything is working. So again, this thing can be used to, you only need 3 pins actually on the ATtiny, and you know we've got 6 of them, so that leaves actually 3 pins free for other stuff, and we can actually output and latch up 8 different outputs as well on this chip too, just like the one before. The one before worked on a different principle. It had, you address 1 bit at a time, and it had 3 address bits that it would decode and so on. But the effect can be very similar, and the outputs of the chip can actually you can draw up to 15 TTL, LSTTL loads with it, so it is plenty enough to drive some LEDs. Okay, so that is what this chip does. And if you look at the data sheet for this chip, you'll see that it has 8-bit serial in, parallel out. It can run from 2 to 6 volts, so it does run on 3.3 volts as well. If you're using a 3.3 volt microcontroller, not a problem. And well, power consumption, good for when you are using batteries, I guess. And I don't have too much else there to register to mention here. This is kind of like a functional diagram. Bunch of flip-flops on the end there. Pinouts. We've kind of already gone through that a bit. And then there is it shows you how the signals relate to each other. The clock, serial data. This is the latching information and so on. And the outputs. Okay, so on to the next type of chip to interface to. Okay, so another option is to use a 74HC574 which is actually a analog switch or an analog multiplexer and demultiplexer. So this would also be able to be driven by an ATtiny or small microcontroller, or a big one, doesn't matter. I did a video on that, and you will see it over here. How can we use a 74HC574 analog switch IC? I would refer you to this video if you want to have a look at it. It would operate pretty similar to what is shown in the video there, except you would connect it up to a microcontroller. It has 4 inputs, and you could then connect some of the outputs, to the other 2 remaining inputs on a ATtiny, for instance. And what is unique about this thing is that it can handle analog signals as well as digital signals, if you like. So I refer you to that video if you want to have a look at it. That would be another option to use with a microcontroller to expand its usage. Okay, so another way to expand the I/O on your ATtiny or small microcontroller is to use devices that can talk over the I2C protocol. I2C was originally invented by Philips in 1982, I think, if I remember correctly, and it was done in order to make it easier to connect devices on their PCBs on TVs at the time, because if you got lots of parallel traces going from one chip to another on the PCB, that can take a lot of PCB real estate just for the traces, and they all have to be of the same length and everything. And well, so they decided to let the chips talk to each other via a protocol, and just a serial protocol. So the ATtiny, if you look at it, it's got on PB0 it's got a SDA, and on PB2 it's got SCL, and these are the I2C protocol pins. It just uses 2 pins. One is a clock and one is the serial data. but there is a little protocol associated with that, so it is not just a simple serial interface as some of the other chips that we've used has done, that you can just use like a shift out in Arduino. Okay, so at this stage now we have had a look at some to expand I/O on microcontrollers that have relatively few pins available, like the ATtiny and even some of the little child boards from Seed Studio that have they are small and they have less pins available due to that fact. So there are actually specifically devices made for that. We've looked at some CMOS TTL sort of type devices like shift registers and latches and so on, but they were output only, and this device here can actually handle input as well as output in a clever way. So this particular device is an 8-bit expander. There are 16-bit versions available as well, as far as I know. This device uses the I2C bus for communicating, which means it's a little bit more advanced than the standard just a serial pin that some of the other devices that we looked at had. But it does make it more difficult to interface to, of course, which we'll look at. This device can run at 2.5 to 6 volts, so if you have a microcontroller that runs on 3.3 volts, then you are also in business with it. Now, what it actually does is it has what they call over here, as I have highlighted, they call that a quasi-bidirectional I/O. Now, how that works is that you can actually set the outputs of the pins to high, and internally it has a high impedance pull-up, if you like, and the idea is then you can actually read back from those pins, and of course if there's nothing connected you'll read high, but you are allowed in your circuit to pull those pins low, and then of course they read low. So that is kind of how they deal with the input. And in our circuit that we're going to look at in a minute, that we have for demo testing, we have connected up some dip switches and so on to ground, and we can then read those when they are on and so on. Now there is a thing to be considered though, that because you can set the pin to high and you can pull it, connect it directly to ground without problems, the other way is not correct. If you make the pin low and then you would connect that pin to like VCC or something, you will damage the chip. It'll be overloaded. So keep that in mind. So that's kind of the way it works. That's the caveat of having quasi-bidirectional I/O. And now it also says that it has high current drive capability, directly driving LEDs, and each pin can be used as input or output without the use of data direction control signal. So as I said, it's kind of clever what they've done. So what I've actually done is I have created a little circuit here on a breadboard, which we'll look at in a minute. We have our ATtiny, and of course there are a couple of pins on the ATtiny that are dedicated for being for I2C, but having said that, there is no software inside of the ATtiny to actually run the I2C protocol, so you have to use an external library for that. So let's have a look at the to remind us. Where's the, oh, here's the camera here. So this is the pin out of the ATtiny, and you can see there is a SCL and an SDA. They are the two pins recommended for I2C, which indeed will do, just PB2 and PB0. Note that that is pin 5 and pin 7 physical pins, but when I say 0 and 2 in the software, it means PB2 and PB0, not the physical pin numbers. And for the serial I/O, we're going to be using PB3 and PB4. Okay, so because we want to be able to use the serial monitor in the Arduino. Let's get back temporarily to the circuit before we look at this. This is the actual thing hooked up here. So yeah, so we got the ATtiny here, and we have P2 and P0, which is PB0 and PB2, connected to the SCL and SDA. Now you do need a pull-up resistor 4.7K for 5 volts. If you're using 3.3 volts, that value would change. And if you look online, I think the Texas Instruments actually has a page with on their datasheet there that allows you to calculate the values that you need for these pull-up resistors for the I2C bus. If you use one of these little boards, which we'll look at in a minute, I've got one connected up to a ESP32 chow board here. You don't have to worry about that. They have that taken care of on the little board itself. Anyway, so we got that connected. A0, A1, and A2, of course, are the address of the PCF8574. These A1, A0, A1, and A2. We're all pulling them low. That actually means that the address that it's going to be looking for is 20 hex. And the output, there's 8 pins for output and input. We've got P0 to P3 connected to dip switch, which is connected to ground. So if these switches are closed, and we will be setting those pins high, but when we close the pin, they will be pulled low. So when we read back from it, they will show that the actual setting on the dip switch. Now keep in mind, we're just doing this as a test. This is not necessarily a circuit that is all that useful, but it is useful to show how the chip works. P4 to P7, those 4 pins, we're actually using 3 of them we're using to output to an RGB LED, blue, green, and red. Common cathode, 330 ohm resistor going to ground, and we do have a switch on P7, a little push button, just for testing. So when we push the button, the idea is it will read the switch and it will change the colors or whatever on the turn the LEDs on. So that's what we have. It's a relatively simple circuit, but it's good for testing because we've got 3 output pins and 5 actually pins that are going to be used as input. Here we have the circuit wired up. Here is an ATtiny 85 that I already programmed with some code, which we'll look at. This is the PCF8574 chip, and here is a dip switch connected to it, as you saw on the circuit. And this is the pull, the resistor that actually drives the LEDs on the cathode. This is actually a little board with a little push button on it, which is convenient. It's got just a couple of legs on there, and that is connected to P7 on the chip. These are the pull-up resistors of 4.7K, and that's really all there's to it. I poked in a few little capacitors here just in case. to absorb any noise or glitches or something. And we have an FTDI board connected here to the pins 3 PB 3 and 4 to show that we can do serial I/O, but the ATtiny itself can't do that directly, so you need one of these little FTDI boards to do it. And this connects to a USB port which actually powers the whole thing. To program it, I've used this thing here. If you look at the part 1 and part 1B, I think part 1B is the one where I actually built this thing as like a little kit. I didn't put all the sockets in there because I'm not planning to work with any of these larger ATtiny chips, but if I ever do, I can just have solder a socket on there and it should work as well. So this is for the ATtiny 85, this is 8 bits. It has some resistors here for those LEDs and so on. And it's fairly simple, and it's connected to a Arduino Uno underneath. It's like a little hat there, and it seems to work pretty conveniently. I kind of like, it's got an old-fashioned plug on there, which is convenient to plug in and out, because what you actually have to do with this is to remove the chip from the breadboard, plug it in here, program it, and then plug it back in here and then test it. So it's convenient to swap that around. Now, so let's have a look at that. I did find some caveats with this ATtiny in the Arduino world. Let's go over here. Let's get rid of that. So this is the actual code. Maybe I'll make it a little bit larger. Okay, that might be a bit easier to see. So this is a little test Arduino sketch program, whatever they call those. In order to do the I2C programming for the chip, in the I2C protocol, I should say, I've actually created a TR PCF8574 code, which can actually be put into the library, Arduino library, if you want to. It is actually based, I found that the ATtiny, that most of the libraries don't work with it, and on the internet you see people talking about ATtiny core, and then supposedly the wire thing works and so on, but I find that this is the Arduino IDE 2.21, and none of that stuff seems to work anymore, and that ATtiny core thing doesn't come up in your library manager at all. So we have PCF8574. There are a bunch of different libraries here, and none of those will really work because they use the so-called wire library that most of the microcontrollers use to do I2C, and it does not work with the ATtiny. So I found that this one over here, Easy PCF8574, was the simplest and the most rudimentary. A lot of these, like the Adafruit one and so on, they use the wire library, and the wire library calls to wire, and it is really ambiguous how the code works, and the story is that you have to use the ATtiny, is it on there? no, it's not ATtiny, it's just tiny wire M by Adafruit. This is supposedly originally done to create a replacement for the wire library for the ATtiny. So I took that other library and I didn't like the looks of it, and in actual fact I modified it so much that you probably wouldn't even recognize it anymore. And this is the actual code. It uses the TinyWire M, and this is part of the TinyWire M. If you go to the Adafruit GitHub thing, USI TWI Master 8, it uses that internally. And I have got a bunch of methods over here. Set the PCF address, which remember that was like 20 hex because we got to set the 0. You can write values, you can invert bits, you can set bits low, you can set bits high. This is on the PCF chip there. Read value, read a bit, and start I2C, and so on. And this is the code. You see internally it uses TinyWire M to do all the work. So this is what you're going to be needing in order to use the I2C protocol with the ATtiny. If you're using an ESP32, you don't need any of this stuff. It will just work with the standard libraries and stuff like that. So that is what we have. And also the ATtiny doesn't have serial, so you can't say serial print line like you see over here unless you use the software serial library, and which is what we're going to be using. That's what that little FTDI board is for. So we can do the receive pin, the transmit pin, we can set those if has to find them. The PCF address is going to be 20 because, you know, remember we're pulling A0, 1 and 2 low. And we are implementing the software serial, and we're calling it serial, so it looks exactly the same as the serial output normally does on a different microcontroller. The library that created is TR PCF8574, TR standing for Tech Relief, which is my little company that I have. Set that the PCF address and the initial output is going to be set to 0. So we will begin. We start the I2C. If it comes back with an error, we just print this error message and make it hang because there's nothing else to do. And the initial value that we actually set on the PCF chip is to write as output is 10001111. And how that works is, remember on the circuit we got bit 7 connected to a push button, so we got to pull it high, so when the push button is down it can pull it low. The other 3 that are 0 are actually connected to the LED, so the LED is off to start with, and the other 4 bits are connected to that dip switch. Again, they got to be high and stay high, so that when the switch is on, we can read it back. When it pulls it low, we notice that it has that the switch is on. I put a little bit of information here that explains a little bit of that. If I'm not clear, you can actually hold the video if you like, pause it and read that if you want to know the deal on that. It's a little bit tricky because the output of the pins of the PCF8574 are actually used as input, if you like, to those switches, and the switch is going to pull it low, but then we read it back as input. So therefore we are when you want to change the output of those other 3 pins over here to turn on the RGB LEDs, you must make sure that these bits stay at 1, and you'll see that happening in the code here. So we read the value from the PCF chip, and if the most significant bit, which is connected to the push button, is actually 0, which means the button is pressed, then we've got some work to do. Otherwise, we just don't worry about it and go around in the loop. This is some debugging information here. Of course, we want to see what value it read, and then we say, okay, if so the new value, as I said, we've got to keep those bits high, 8F, which is actually what the same as that value over here. So we are ORing it with 8F to make sure that those bits stay high, otherwise the system will get confused, because we won't be able to read the switches and so on. Now, if the bit 1 is actually low, which means that the we're only reading 3 of the dip switches here, the fourth one we're just ignoring. If number 1 of the dip switches is actually on, which means it is going to pull that signal low, then we want to output the pin. So we OR new value with 10 hex, which is actually the bit for the blue LED. If you look at the circuit, just to remind us, you see pin 4, and if you look at that, 0, 0, 0, 0, 1 would be 8, and it is connected to the blue, and pin 5 is connected to green, pin P6 is connected to red. So that is why we are actually using 10 hex in order to turn it on, and if we turn it off, we want to end it with the ones complement, which is EF, which is all the bits are on except that particular one, so therefore we're actually turning that bit off. Now, I do have under the header here, there are some set bits high and set bits low that could have been used, but since we are fiddling with the values here, I found this for me that worked. But if you find that hard to follow, here we could have had PCF write bit or set bit high, and the bit number would have been 4 and 5 and 6. 7, 6, 5, 4. So we create a new value, we then write that away, so now it is updated, and for just debugging purposes we are printing the new value just so we can look at it. We delay 250 milliseconds just so that gives us some time for the button to settle and to be released and so on. So we don't, it's like a bit of debouncing, and that's it. So does it work? Well, let's have a look. Okay. So now if I push this little, if I switch number 1 on and push this button, and maybe I'll take some of the light away so it'll be easier to see. So now it is blue. Switch number 2, push the button, green. Switch number 3, push the button, red. Of course, to my eyes it's really red, but the camera always makes it, it likes red and turns it into white. So if I turn 2 of them on, push the button. So now we have red and green on, which really kind of looks yellow is from a distance, and if I turn, now all three of them are on, so red, blue and green are on, so it is all working. Okay, here we have an ATtiny 85 connected to a shift register and also connected to an I/O expander, PCF8574, which is actually on this little board here. Because we're using that little board, it has pull-up resistors on there, so we don't have to add those. We normally would have to add a 4.7K pull-up resistor on the ATtiny SDA and SCL ports, because it is very sensitive for that, but this board has taken care of that already. And connected to that board we have a keypad. So if we look at the actual circuit, this is what we have wired up. We've got the ATtiny, and we have the shift register over here. The latch is connected to P1, clock connected to P3, and serial connected to P4. So remember, this is a simple serial interface. This is not I2C, but we have the PCF8574 I/O expander connected to the actual keypad, columns and rows, and P0 and P2 are connected to the SCL and SCA. It does use the I2C interface. So here we have an example of using ATtiny to do both some form of serial interface to this chip over here and I2C to that chip over there. So this is the input. Now this is interesting because we are using the PCF8574 both in input and output mode. The actual chip has a quasi input mode, in which that when you set the ports to high, and I've shown that in another section of this video where I connected some dip switches and so on to it, but if you pull the outputs high, it has a high impedance pull up internally, and you are allowed to pull it low. So therefore, and then when you read it back, if you put an external circuit on there, in this case the keypad, you push a button, something will be registered as low. And in order to read the keypad, it will alternate between output and input on those in order to determine which key is down. Where the row and column intersect, that will be the key. In any case, and we have a little LCD display there where we've got the A, B, C, D, E, F, G. Conveniently, the shift register has got it as A, B, C, D, E, F, so we can match it with the A, B, C, D, F on there, but that's by sheer coincidence with some resistors. Okay, so this is what we have. Oh, and notice that the columns are on 5 to 8 and the rows are on 1 to 4. So then we have some code, and we'll be talking about some of these things here because this was a bit of a hassle to get that working, and that's typical when you're dealing with ATtinys. So the I2C address is going to be 20 because the A0, 1 and 2 are pulled low, and that ends up being equivalent to a code of 20. We're having this particular software is able to deal with different keypads, 3 rows, 4 rows, 4 columns, and so on. The keypad we're using has 4 rows and 4 columns. The actual keys on the keypad are 1, 2, 3, A, 4, 5, 6, B, 7, 8, 9, C, and star, 0, hash, and D. So that's how it knows to equate which keys to what character values. And remember when I said that the rows are actually pin 1 to 4, but it goes, it actually in the key, it counts from 0, so it comes 0, 1, 2, 3, and columns 4, 5, 6, 7. And then that actual keypad library has a function called make key map, so we give it how many rows and columns it has, and the address, and that we're actually dealing with a PCF8574. The 8575 is actually the same thing, but it's 16 bits wide instead of 8 bits. So if you want even more input and output pins, you can use the 75. Anyway, we have the latch, clock, and serial for the shift register connected to pins 1, PB1, PB3, and PB4. And I created a string which is a code lookup because this particular keypad comes back with the actual character codes. The previous example I did on the ESP32, it actually came back with key codes. So therefore I'm using a string here and doing an additional lookup of that. So now we have a little function that says get key code to get the character, and I am just using the since it's I created a string, and the string object has a index of, so index of the key, so it will be 0 to 17 depending on what code I give it. I added a few extra values here, E for error and B for blank, which if it's a space, and you see the spaces on the spaces on the end there, so it's going to be 17. If for some reason it comes back with a code that's less than 0 or more than 17, which could happen if you give it a key code that doesn't exist, I think it probably comes back with -1 or something. I'm just guessing, I don't know. I'd have to look at the documentation, but usually that's the case. Set up the output pins there, and then we've got keypad begin. Now the keypad code internally calls the tinywire library, so it actually deals with setting up the I2C, and I'm displacing the key for space, which remember is going to be blank to initialize it. And then we have a little thing here to take up the character key. It does the key code, does a lookup on this table here for which segments to light up on the 7-segment display, and therefore it will do it sets the latch to low on that particular 5 shift register, so it disables the output while we're fiddling with it. Then we shift out the 7-segment values, and then we set the latch to high again to display the value. And here, if there is a key, then display it. If not, they just keep looping around. So if we look at it, we've got it here, and we have the keypad over here. So if I press 1, there we go, that's 1, 2, 3, A, 4, 5, 6, B. B again, we put, looks like the 6, but I turned on the little decimal point, as you can see, 6, B, 7, 8, 9, and C. And then we've got a star. Well, there is no star on the 7-segment display, so I created a code. It's going to be H0, and here is a hash. It's looks like an 11 with a little decimal point on it, just so that we can distinguish it. That's all. This is just a test, right? And this is a D. So that is working. Now, in order to make this work, this is exactly what happened. Okay, so if you look at this code, you will notice that I've got a keypad tw.h. This is actually a library that is on GitHub, and I think we can show that over here. And this TW version here is actually for the ATtiny. So I found that online, and I therefore I tried to install this library. I downloaded it. If you go over here, you can say code, download the zip file. So I did that, and I thought, well, maybe I can go and use this at zip library. And so I went down there, and there it is here. So I said, okay, open, and no show. Error, internal library install failed, moving extracted archives to destination, dir library not valid. Whatever that means. So therefore I decided, well, I will take the actual code and move it to my folder for the actual code. So we've been looking at Tiny PCF keyboard, So I put the code in here, and then what you do is you tell the code, you put it in double quotes instead of those little angle brackets, and that tells the compiler to look for it in the same folder as where our main code here is located. Okay, so then in the library manager you find that there is a keypad library that you can actually use. It is also available on GitHub as well. Let me see now, where's the, oh, here. This is, so you can actually get to the code from GitHub as well, but it exists in the actual Arduino IDE as well. So I didn't download that from here, I just installed it using the button over here that said install, so it's already there. So therefore that one here is going to be there. TinyWire M also comes from here, so that's all fine. But then when you do that, you will find that you will get errors. And this is the one thing with the ATtiny and this TinyWire M file. It has gone under several revisions, and originally for some reason, which wasn't a very good idea, they renamed the two functions, that is actually write and read, to receive and send. The developer probably thought that was more appropriate or something, but it also made it that the TinyWireM library was incompatible with the wire library. So since then they have changed that. I think Adafruit did that, so that they do have read and write, and for some reason the code, the way they're using that, did not compile. It complained that the read, I think it was the send, yes, the send function did not, was not available, and you can see that over here, those two statements over here. This is the file as it came from the downloaded or from the GitHub. It had send and it's got receive. That was for the old version, and so I've been reading in the Adafruit GitHub page as well, and they actually said, oh, we have, one of the things was we have added the read and write functions to make it more compatible with write with the wire library. And so I had seen that and I remembered that, and I thought, well, if it doesn't know what to do with send, I'll change it to write. And then I thought, well, for good measure, I'll change the receive to read as well. And that's what I did, and now it works. I have no idea why send didn't work, because it's supposed to be still there, but it didn't. And so that is another thing that I had to do, and that was only because I actually remembered seeing something referenced to that in the Adafruit thing, that I got a clue there to what I might have to do. Anyway, so that is that. We actually were able to make it work on the ATtiny. So that is another little test here that actually was successful, and it shows the use of both of these chips over here being used on the one little ATtiny. And in fact, we still got one I/O pin left, which is PV5. Anyway, so much for that, and gives you a bit of an idea how this stuff works. Now, when I did the same thing on an ESP32, I didn't have to do any of that. I could just use the standard libraries and it works straight away. So just a heads up on that.